So in today's video, we're going to be doing improper integrals. So first off, what is improper integrals? So we know that we have, when we do an integral, there's like the basic integration, and then there's the one where we have the boundaries, where we have a to b, and we call that definite integral because we have the values there. So for example, if I have like 1 to 3 of x or 2x dx, for example, right? And what we often do is we have to first figure out what the integral of 2x is, which is just x squared, right? And then we have to input the bounds in, so we basically plug in the upper bound and then subtract it by the lower bound. And then we get an answer, in this case 9 minus 1, something like that, and that's a definite integral. Improper integral is when you do have the boundaries, but instead of having a boundary from a to b, instead you have something like a to infinity. So as you can see here, we have the bounds from a to infinity. So in these scenarios, what we usually do is we want to take the limit, and then we have to say, okay, we do any sort of value, so we can call it b. So we let basically replacing the infinite sign into a value. So we have that change it into b, and then we basically plug in the infinity value. So this is something that you want to do, and then it works the other way around. If you have the negative infinity on the other side, you do the same thing, and then this time you basically plug in the same place. So that's kind of the idea. So basically, when you see improper integrals, what you want to think of is take the limit. And then in the last scenario, we have two bounds that are both infinity. So what we want to do is we want to take the limit, but before we do that, we want to split it into two parts, so that we at least have one that is not an infinite value. So we basically replace it with any value, so we can just call it c, right? Because remember, in previous video, we know that when we have the bounds 1 to 3, that's basically, oh my gosh, what is happening? F of x, right? What we do is we do this is the same as this. These two are the same thing. So that's kind of the idea of what we're doing in the third scenario, but now let's actually apply it. So in improper integral, we want to determine whether they converge or diverge, but that doesn't really matter for now. For now, let's try to actually solve it. So in our first scenario, we have the integral from 8 to infinity of 1 over x times ln of x. So in previous video, you probably already know how to do these by doing u sub, but this is an improper integral. So let's try to do that. You can feel free to pause the video if you'd like, but I will be going over it now. So looking back, this is basically the same form. So what we want to do is take the limit. So we take the limit, and basically we want to have a value approaching infinity. So let me just call a. It could be a, it could be b, it could be c, it could be d, it could be anything. I just call it a, okay? And then the 8 remains the same. We don't want the infinite value, so we replace it with a, right? And then we do the same thing. We have 1 over x ln of x. So now let's actually try to solve for this. So we have 1 over x ln of x. How do we do this? So we can use u sub. In this scenario, I want to let u equals to ln of x. Du will be the derivative of ln of x, which is 1 over x dx. So isolating dx, we get x times du. So to solve this, I'm just going to leave the limit as it is. And I want to remove the bounds for now because I'm doing u sub. So I'm doing u sub. I get, for dx, I replace it with x du. So dx is gone. And I have x du times x times, divided by x times ln of x. In this case, we have u. And we see that we can cancel out the x. And we get limit as a approaches infinity of 1 over u du. Notice I don't have the bounds because I'm doing u sub. So for now I don't want to have it, but I'll put it back in later. Okay, so I have limit as a approaches infinity. So the integral of 1 over u, remember that's basically just ln of absolute value of u, right? So now that we integrated it, we can plug in u back in. There's two ways you can do it. The way I'm doing it is I'm plugging u back into x, or you could basically change the bounds, but I want to keep the bounds the same. So I'm replacing u back into ln of x. So my bounds now, I could plug this back in, so that's 8 and that's a. So, ooh, not a lot of space, that's okay. We have that, okay, and then we basically plug it in. Let me just give some more space. Let's move this down there. Yeah, we have more space, okay. So let's just make this clearer. Okay, sorry about that. We have that, right? Okay, and then we plug in, right? We do the same thing, we just plug in the values. So ln of a minus ln of 8. And we will basically want to find out what the limit is. So think about it, as a approaches infinity. Now remember what the graph of ln of x looks like. It looks like this. This is not a really good drawing, but it looks something like this where it keeps growing infinitely. So we know that ln of a, because when it approaches infinity, it will keep growing and growing to infinity. So this is going to be infinity. So this whole thing is going to be infinity. And infinity minus any finite value is still going to be infinity. So our answer is going to be infinite. And when it's infinite, that basically means diverge. So for convergence and divergence, just for now, just remember that convergence is when you have something that's finite value. So like something that is 2 or 5 or 1,000. Divergence is when it's not a finite value. So in this case, infinity is not a finite value, so our answer is going to be diverge. Now let's try something else. So in this case, we see that this is very similar to what we talked about earlier, the third scenario, where we have both bounds that are not finite. So what we want to do is we want to first rewrite this. So we have infinity to, this time I want to call it c, for example. And basically I'm rewriting it, right, so that I have the finite value separated. Remember that these two are literally the same thing. So now what I want to do is then take the limit. So this is basically the exact same process as earlier. So what I do is I take the limit as, this time I call a approaching negative infinity. So I have a to c 1 over 1 plus t squared dt plus, let's use another value, let's say b to infinity, and then we have c to b. I know with all the letters it can be confusing, but it's just a way to define values, so it doesn't really matter what letter you choose. So now that we have that, now let's actually try to solve it. So first, how do we integrate 1 over 1 plus t squared? Remember, if you look back at trigonometry, 1 over 1 plus t squared is basically the inverse trig. So this, the integral of 1 over 1 plus t squared is tan inverse of t, right? And we know 1 over 1 plus t squared is tan inverse, and it's the same on this side as well. So now all we gotta do is just plug in the bounds. So I plug in the bounds, I get tan inverse of c minus tan inverse of a plus the limit as b approaches infinity of tan inverse of b minus tan inverse of c. So c is any number. So for now, I'll just leave it like that. Now for a, because right now the limit is approaching negative infinity, what we want to do before we do anything is first take a look at what the graph of tan inverse looks like. Remember, tan inverse, they are bounded because the original function, the range is infinite, but in the inverse, it's opposite. The range is limited. So remember that towards negative infinity, it approaches negative pi over 2, and towards positive infinity, it approaches positive pi over 2. So in this case, we have a approaches negative infinity. So as tangent, this is the function of tan inverse. As it approaches negative infinity, it approaches negative pi over 2. So we have negative pi over 2 plus we have the limit. This time it goes to positive infinity. So we have tangent towards positive, inverse tangent of x as it's going to positive infinity, it's going to approach pi over 2. So we have pi over 2 minus tan inverse of c, which is just a number in this case. So let's just remove the brackets. So we get tan inverse of c minus minus becomes positive, right? I'm just really simplifying this. And notice this beautifully cancels out. The tan inverse c beautifully cancels out, and we're left with pi over 2 plus pi over 2, which is basically 2 pi over 2, which is equal to pi. So now we have a value pi. So what does that mean? Remember, the question is asking if they converge or diverge. Remember, convergence means that it approaches a finite value, and pi is a finite value. So our answer is that it will converge because pi is finite. So there you have it. That's an introduction to improper integral. Thank you for watching. I hope this helps.